Okay, back up, I guess. So here's our circuit that we're given. We're going to have a 3-branch parallel network. Our voltage total is 58 volts. R1 is 150 ohms. 150,000 ohms. Yeah. 620 kilo ohms. And 620 kilo ohms. What I want to solve for, what is my resistance total? What is my current total? What is my power total? Then I want to know the individual currents and powers through each of the resistor branches. Because again, if we wanted to go build this thing, we have to take power into consideration to determine what size of resistors we need to get. Yeah, right out of that corner. I wish it, yeah. Been there, done that. Give you guys a couple minutes to kind of work through this, and then I'll call on some names and we'll kind of work through it again. Yep. Yep, just remember using Ohm's law. And that'll find you the individual branch currents. Oh, this will be fun. I don't know what this is going to do. That was a requirement for me getting this job, is I had to have an evil laugh. I was graded on it. My first semester, really. By the second semester, I got the hang of my evil laughing. Computer information teaching is what I minored in, was teaching. So you guys are aware that this question on here does come from the 3-branch quiz in Moodle. Let me look. Third one. And we did go, like I said, we went through all the math yesterday. So all those quizzes you should be able to at least attempt. If you do have questions, like I said, please feel free, ask them in class, after class, at lunch, via email, via text. I'm here to help you guys. Okay, I'll give you guys about 2 more minutes and then we'll kind of start. Obviously, I get that I'm not expecting you guys to get this master to where you can solve these problems in about 5 minutes. At least just kind of get started. You can continue to work while we're discussing this. All right. So first step we want to solve for is our total. Carson, you are up first. We want to solve for our total. How do we go about doing that? Okay. So when we do this, we should expect to see a value less than 150K to start with. Okay, Carson, what'd you get?
I got 1.39. I don't know. Yeah, I got 1.1. Yeah.
Got 101K ohms?
No, I'm multiplying.
That happens. Okay, about 101 kiloohms. Okay, let's see. The good news is it's chewing up your times off the wheel. So it takes them up and removes them off. So Carson, we're going to go with you again. Okay, so what's the formula for getting our current? Okay, also using Ohm's law, what's our formula for that? Yep, so the voltage total divided by the resistance total will also give us the total current. So we take the 58 volts We divide that by the 101 kiloohms. Micro?
Do you know it's through your calculator and engineering notation is 6?
Yeah, it is.
Oh, it's so nice.
If anybody needs help with that, I can help you after class. Yep. Yeah, so I'll show you afterwards. You can bring your calculator up and I can help you try and find it. Another good resource is download the manual for your calculator and have it on your computer or on your phone. It makes it really nice when you're trying to figure out where is this function on my calculator. I have the TI-83 manual downloaded to my computer and then also on my phone. Okay, 574.25 microamps. Oh, where'd my mouse go? There it is. Third time. Carson, you're up again. I'm just kidding. Jessica, you're up. So the next thing we're going to look for is power. Come on, scroll up. So Jessica, to start with, what is our formula to solve for power? Current times voltage. Okay? So we have 574.25 microamps and multiplied by our voltage, which was 58 volts. How much power does that give us? Times 10 to the what? So let me see.
If you put in engineering notation, it'll give you something out in
Okay, yeah, so part of it is, so you got 50 or 574, you need to have that times 10 to the negative sixth. So that will shift the number down. Negative 10 to the negative 6 because it's micro. Micro is 10 to the negative sixth. Is that better? Did you get 33 times 10 to the third, or 10 to the negative third? 25 microamps. It's a U with a tail. A front tail, I guess you could say. So 33.3 milliwatts. So, do what? Yep. So another way to think of this is, so when we look at our total power, we only have 33 milliwatts of power total in the entire circuit. So right off the bat, that tells me that we're not going to have huge powers on these guys, so I will be fine with whatever resistor I can throw in there. A quarter watt, an eighth watt, anything, it's going to handle it just fine. Because we have three resistors, and it's going to split up that power between those three guys. So that's the total amount that we're going to have in the circuit. Same thing there too. Mm-hmm. Yeah, both of them, based on your thing. It's easier to get, this is good. This is an easy way to get higher currents because you're reducing your overall resistance load. So parallel is easy to get current. Series is easy to get voltages. Okay, current through R1. And the lucky winner but see, here's the good thing, like I said. This yeah. It's deleting them. I got it this time. Because the last time it landed on Carson, it deleted it, and then it was pointing on Kately. So, yes. Okay, so the current through R1, how do we solve for that? Ohm's law using what? Voltage over resistance. So how much voltage do we have? 58 volts. Over how much resistance? And that gives us how much was it? Microamps. Okay, so one thing we should also notice, this has the smallest resistor value, so it's going to have the most current. And if we look real quick, 386 out of 574 is going to give us about 180-ish left over for the end. So we know that at least we're in the right ballpark. So far, everything's tracking with how it should be. Smallest resistance is going to have the most amount of current. Seth. Power for resistor 1. So current and voltage of R1 multiplied together. Okay, again, we have the majority of the current on this resistor. We're going to have the majority of the power on this resistor. Okay. Current through R2. Colin, you're up. Okay. Let's see, this one was, the resistance was 620. Okay. Everybody agree with that? Disagree with that? Sounds close to being right. So the way that we find these currents, remember, is we're looking back just using Ohm's law. So the voltage drop across R1 divided by its resistance of R1. Voltage drop of R2 divided by the resistance of R2. So when we come back and look and remember, these guys are all in parallel, so they all have the same voltage. Because they're all in parallel with the supply. They all have access to the full 58 volts. So, which is also what we should expect. Like I said, the value that I was just kind of roughly calculating was if we had 386 microamps here, we're going to have about 180 microamps left over, give or take some change. Half of that is going to go through here. And the reason I say half is because both of these resistors are the exact same value. So they're going to split whatever is left, and they're going to split that evenly amongst themselves. Neither one is going to take more than the other because their resistances are equal. So, knowing that, we can also go through and we could calculate the same values for IR3, but we've already done the math. So right here, we could also just label this as IR3 because it has the same voltage, it has the same resistance. We don't need to demonstrate a second calculation for the exact same value. We just make sure we tag it as such. So in this case, we can know that. The other way, like I said, we could have solved this is when we come down to it, because they are both the same value. It's going to split, whatever's left is going to split evenly between them. So we could have gone IR2 is equal to IR3, which is equal to the current total minus the current going through R1 divided by 2. So in a formula, that's what we would look at. How much current do I have left after the first branch? What's it going to split? Well, it's going to split between these two. It's going to split even, so I can just take that and divide it by 2. And in the instance, we're going to get the 93.548 microamps. And also the same thing's true with power. Okay? We have our power total subtracted from the power that's being dropped across R1. Whatever's left, we're going to split, and that's going to give us how much power. So with that, who's going to give us our answer for the powers? Simon, you're up. Okay, so like I said, you've got either one of these two methods you can use from. So the power from R2 is going to be equal to the power from R3. So which formula would you like to use? Do you want to use your total current subtracted off, or do you want to use Watt's law? Watt's law, okay? So the power of R2 is also equal to the voltage of R2 times the current through R2. R2. So if that's the case, how much voltage do we have across that resistor, Simon? 58 volts. And how much current do we have going through that resistor? R2. Right here. Because we did just find the current through R2 already. 93. So that's what I'm saying when we're going through these notes, and I don't do the greatest job with these. I try to box them and everything. But when you get your answers, make it obvious that that's your answer. I like to box the answer and what I'm solving for. That way when I go back through my notes, I can quickly find stuff. I don't always do it when I'm doing in these notes, but I try to. So it's just a good skill to develop into. So coming back to here, we have our 58 volts. We're going to multiply that by 93.548 microamps. And again, micro is times 10 to the negative 6th. We plug that into our calculator, and that's going to give us what? And I'll wait. And Simon, when you get that plugged in, let me know what your answer is. And then times what? Okay, so you got your 58 times that value, right? So 93,548 times 10 to the negative 6th. So I think you're off just a hair on your decimal points, unless I wrote the number down wrong. I think I wrote down the decimal point wrong is what I did. Sorry, Simon, I put the decimal in the wrong place. So did you get that calculation? Okay. So we got 5.426 milliwatts. Okay, so now we can also say that is going to be equal to power of resistor 3 as well, because the voltage is equal and the resistance is equal. So the current's going to be equal. Everything in that is equal, so we can use the same calculation for that value as well. Then, just to double check, we can go back through and we can add up our values that we calculated to make sure they add up to what we calculated for the totals. So for power, we have 22.426 milliwatts. We've got 5.426 milliwatts. So across resistor 1, across resistor 2, and then we're going to add in another one of this value for resistor 3. And we end up with the 33.278, which is 33, again, what we matched there for the 33.3 milliwatts. The currents, we can add those up together again. And honestly, since the resistances have matched up every time, our power's matched up pretty time, I feel pretty confident that our currents are going to match up within a few, within a few decimal places because it's rounding. They do match up? That's what I like to see. Okay, so like I said, so parallel circuits are a little bit different than series circuits. You just have to adjust how you're thinking about them just a little bit for the resistances and the currents. So, series circuit, what's the rule for series circuits? Resistance adds, voltages change, and they'll add to your total voltage. What about the current? Current stays the same. What about power? Power adds together. So in a series circuit, the current will stay the same. Voltage drops will add up to equal your voltage source. Your current will stay, I already said that. Current will stay the same. Resistances will add, and power will add. Okay? In a parallel circuit, current changes, voltage stays the same, resistance changes depending on what it is. What about power? Power changes. It's going to add together. The resistance, we're going to use the reciprocal method versus just directly adding. It is crazy annoying. Wait till I get to capacitors. They're the opposite. So transistors are not necessarily bad. It's all the different configurations you can have. That's where the confusion gets into, and it depends on how you want it. You can get it to build an amplifier that inverts your signal, so it'll give you a positive 5 volts. If you have a positive 5 volts coming in, you amplify it, it's going to give you a negative voltage out. And then when it gets a negative voltage, it'll give you a positive. You'll actually invert your signals. It all just depends on what you're using them for. There's pros and cons to using all the different types. Okay, is this making sense or starting to? Barely? Okay. Let's run through another example. Why is it not doing that? Review. So I'm not trying to tell you guys all these things just to scare you. I'm just giving you a heads up of what's coming. Is there any problem with drawing this circuit like this?
It's not going left or right, so it doesn't like it.
Right. It defies convention.
Is that VI?
VS. Voltage source.
Oh,
2200. And 240. Yep, just regular old boring ohms. Yeah, resistance total, current total, power total. Whoa. I hate this board sometimes. So in this circuit, the resistance we're going to be looking for is going to end up in ohms. Current is going to end up in milliamps. Power is going to end up in watts. Just so you guys have a point of reference for those. So again, I'll give you guys a minute to go through this. We're going to go through the same steps as we did before. I don't care the order you do these, because some of these you can do a little bit different. And so what I'll do is, like I said, I'll give you guys a chance to go through and solve this, and we'll go through and answer. I'll give you your choice of what you want to answer in each of the categories. So one's for resistance, current, and power totals. Then once we get all those solved, then we can answer the branch currents. After we get that solved, we can solve for the powers. Yeah, Carson, we have been picking on you a lot. 2. Yeah, you're on there twice. Yes. Just group the wheel by name so that way all yours are clustered together. Well, 3 of them got eliminated today, so. Now I try to use the same wheels day to day. I might add more, like the next day, but I try to spread out. Well, like I did say, if you're absent on days or whatever, and your name gets drawn, then your name gets added on in that additional time. And I've actually had that happen. Like we got down to, let's see, what was it? My first class, I pulled this out. There was I had a class of 13. I think there was 4 people left on the wheel, and 3 spaces were one name, and 1 name was all the other ones. And I was waiting to see how far down it would take before it evened out. That one actually got down to where there was 2 of the same name on the wheel twice, and that's all was left. And of course, I had to spin it because,
You take 6,
I do. But that's one of the joys of teaching. As you feed off of your students' pain and misery and sadness. Drink from their tears of sorrow.
Why she comes home and straightening me out too.
Because she didn't get enough at school.
Apparently my dad doesn't even have a school though, because he comes in and he's still
So both your parents teach?
Yeah, at the same school. I thank the Lord every day I can go to that school.
Which school do they teach at?
Lake Hazel Middle School in Maryville. They're history teachers. Well, my mom's 7th grade, my dad's 6th grade, but yeah.
That's
the best time to be a teacher. Because you can pick on them while they're going through puberty. All the boys don't fall until you give them a loan, is what my mom says. She's made a plethora of them cry. But she said girls are super mean. She was alright, actually.
my aunt, not my aunt, my sister-in-law. She teaches down in Malata as well, and she's had her kids as the students. She's one of the English teachers down there, and she said it's hard because, for one, you have to be their teacher. You can't be their parent at school. It doesn't work. You have to separate it, and then you piss them off at school, they're going to be pissed off at home. And, in that aspect that they can't separate, mom the teacher versus mom the mom. And there's been times where they've gotten to some knockdown drag out fights. But at the same token, then you have your mom or you have somebody directly on your team in case something does happen at school. They've got a lot more fighting power for you there. So usually they can keep you from getting in too much trouble.
So then I would just be like, God, my English teacher is worse. That's so much homework.
Oh, he would do the son would do that all the time. He would come home and always complain, post on Facebook, my English teacher sucks. All right. Let's go ahead and start solving this. We got a couple minutes left. I know we won't finish it, but we'll at least get a couple of answers and kind of go from there. I wasn't ready for it either. Jeff, which would you like to solve for? The resistance total, current total, or power total? Okay. The reciprocal method, okay. You write this out. Okay. 6, 7, 8? Again, that's why I ask. We good there? Just ohms. Because none of these are in ohms. I mean, none of those are in kilo ohms. Okay, Seth, which one would you like to solve for? Current total or power total? Apologize, my battery's starting to die on this pen. This is not funny. Stupid battery's dying.
That'll give you 366.5
Point how much? 366.5 milliamps. We good there? Okay. Before I go any further and make a bigger fool of myself, we're going to call that good for this time. But don't worry, there'll be round 2 tomorrow. We'll finish up this problem. And like I said, and then we're going to start in on a current meter. So kind of an application of parallel circuits. Not kind of, it is an application of parallel circuits. Okay, remember, we do have quizzes that you guys can take.